While I'm sharing this screen, I should say I've got my Taste of Nuclear Physics t-shirt on, but it's too cold to not wear a jumper in the UK today. So,
That's fine.
okay, thank you very much. Yeah, so my talk is closely related to the one Alison just gave. I'll be talking about work mostly from Argonne National Lab in the US. And what I'll be addressing is our studies now that have been going on over many years between sort of myself and other people at Surrey, the CEA Saclay Group, Argonne National Lab, and also Oak Ridge, where we're looking at Coulomb-excitation of refractory isotopes. So what refractory isotopes are, briefly, are ones that have their chemical properties mean that they don't escape from traditional isol targets that we use for radioactive beams. So this is why I've said these were hitherto inaccessible. These can't be addressed, these kind of studies can't be done at places like Isolde just yet, but perhaps in the future that will be possible. And the reason we do that is because there's lots of interesting physics in this region. So this nice picture just here is from some of the early work we published back in 2017 on 110 ruthenium, and it was highlighted as one of the US DOE science highlights. I always found it very strange, when you went on this website, there was sort of gravitational waves, and there was some, nice bit of nuclear physics, or a slightly niche bit of nuclear physics just below it. Okay, so this is the region we're seeking to address with our studies. The present work that I've said in red, present are experiments we've already performed. So we've looked at these cases of 110 ruthenium and 104 and 106 molybdenum. And on the books, accepted by the Program Advisory Committee at Argonne, are these three isotopes. 112 ruthenium, whereas Alison highlighted might be the most triaxially deformed nucleus. Palladium-114, a study that's going to be really informed by the lifetime results from Eugenio and from Alison, and also zirconium-100. So this is the simple picture at the n equals 60 subshell closure, shell closure, where you see this sudden onset of deformation. And the real sort of problem we're looking to address is how does collectivity emerge way away from closed shells, as we're looking at here. There's always been a question, if you look in the literature, about whether these isotopes may be triaxially deformed, which we think they are, or they could even be oblate deformed. And where does that transition point from prolate to oblate occur? Okay, so why do we think that there may be triaxial deformation present in this region? Well, here's some very simple level schemes I've shown just here. And I show the classic examples of triaxial deformation is in the osmium and platinum isotopes. So you see osmium just here. This famously has the lowest second 2+ energy. So in these quasi-gamma bands, this 2+ energy is the lowest of any known nucleus. Why we think that might then apply to the ruthenium isotopes is the next lowest happens to be ruthenium-112, and in 110 ruthenium and 114 palladium, you can see these also have these extremely low energies for these particular excited states. Now, we think this region might be slightly different to that of the sort of well-studied platinum-osmium region. In platinum and osmium, the region where this deformation exists is relatively narrow, whereas in the ruthenium, molybdenum, I should also add palladium to this region is thought to be rather more extensive. It's driven by two particular orbitals, the H11.5 neutron orbital and the G9.5 proton orbital. And I should point out, I think, that this is triaxial deformation at or very close to the ground state. Triaxial deformation is relatively well established in high excitation energy, high spin physics, where we can mix lots of orbitals together, but close to the ground state, it's rather more rare as a phenomenon. So focusing now on the particular case of 110 ruthenium, here are what I've called the empirical conditions. These are things just from energy levels. There's a lot known about the spectroscopy of these nuclei. They can be studied in fission fragments, etc. And what we see if we look at the 2+ energies is that as you follow them, this line with increasing neutron number remains relatively constant for ruthenium. So deformation is staying constant. Things aren't being driven towards more prolate deformation. This energy ratio between the 4+ and 2+ states never reaches the rotational limit. This is in stark contrast to neighbouring strontium and zirconium isotopes, which seem to behave like perfect rotors. and the energy of the second 2+ state falls below the energy of the first 4+ state. You saw on that last slide that I showed how low in excitation energy this second 2+ state was, and this is thought to be a sort of a smoking gun for triaxial deformation according to various simple models. So things already look quite good, so quite promising. So what can we add from Coulomb excitation? Well, the simplest sign is we can look for the B of E2's connecting bands where we change state we change quantum number k by 2 units r. So if we have a very large matrix element connecting the second 2+ and first 2+ states, or similarly the second 4+ and first 4+ states, this is a good sign of triaxial deformation. With Coulomb, of course, we can measure moments, quadrupole moments of states, and for triaxial deformation, we expect these to be reduced with respect to rotor values, but this is not the strongest sign of what we're looking for, but I think it's worth pointing out. And related to Alfredo's talk at the beginning, what we really want to be able to use are the quadrupole sum rules, so these Kummer-Klein sum rules, in order to connect to deformation parameters in the intrinsic frame of the nucleus. And I prepared a few comments about that for this particular analysis in the final slide. So as there's students present and things, I thought I would just briefly skip over a few details of what we're doing with Coulomb excitation. So what this is an interaction that's purely electromagnetic. So it's things we can write down and understand. We understand the electromagnetic interaction very well between the target and the projectile nucleus. We could perform an experiment wishing to either study the target or the projectile. As these are all radioactive nuclei we're talking about, the nucleus of interest here is the projectile, and the target's something that's high Z, so there's a large electric field between the two. Now this is a technique that's been around for many, many years, since the advent of experimental nuclear physics, really. But as I think Nigel touched on in his talk the other day, this has really undergone something of a renaissance, and that's because of radioactive beam facilities. The cross sections are large, so they suit low intensity radioactive beams, and we can also do some very interesting physics as well. Early Coulomb excitation experiments didn't look anything like what you see presented just now. We firstly employed spectrometers, and I think Magda talked about real state-of-the-art Coulomb with spectrometers that people are still doing nowadays, but this was how things looked like in the early days as well. And with just silicon detectors, so not detecting gamma rays at all. This clearly limited with light projectiles the number of states that could be studied to just the first few. But radioactive beam Coulomb is now a relatively mature field. So I show this slide because this was the first radioactive beam Coulomb measurement to make use of the reorientation effect in order to measure quadrupole moments. And this was the case of neutron deficient krypton, so 74 and 76, an experiment performed at Gunneel. So this is the first, in my view, experiment that looks like the ones that we tend to talk about nowadays. Okay, so the specifics of what I would like to discuss then. So as I mentioned, we're interested in refractory isotopes. So this is not possible at somewhere like Isolde. So we have to plan our experiment somewhere else where we can produce a beam of these isotopes. And where we do that is at the CARIBU facility at Argonne National Lab. So what CARIBU is, for those who haven't heard of it, is a californium-252 source. Californium is very nasty and hard to work with material inside a gas capture. So californium-252 undergoes fission. The gas capture slows down these fission fragments, and then there's a bending magnet at the exit of this gas cell, where we can select the mass of interest before charge breeding this in an ECR iron source. You'll see why that was a problem initially in the early days of these experiments, before being injected into the Atlas Linac and being delivered to experimental stations. And for Coulomb, we want a beam energy of the order 4 MeV per nucleon approximately. So what do these experimental stations look like? Well, for the CARIBU measurements we did, we don't use a silicon detector, as is traditional in some experiments you may have seen at Isolde. what we use is this system of PPACs called CHICO2. So CHICO2 is a detector system that's sort of set up and funded by Lawrence Livermore National Laboratory, Ching-Yen Wu, Jack Henderson and people when he was there set this up for these experiments. And for gamma ray detection, we make use of the Gratina tracking array, so the US equivalent of the Agata tracking array. So the particles are registered in these PPAC detectors. We don't really have an energy measurement for this thing. What we do is look for the time difference between the two hemispheres. And as our particle comes in, we scatter. So we have scattered lead and our scattered beam particle. And these are detected on opposite sides of this array. And then the unreacted beam is dumped into a beam dump somewhere over here. And the decay nuclei are measured with some germanium detector, which can tell you things about your beam composition and beam intensity, etc. So this is what the early results looked like with the ECR iron source. Now, the problem with the ECR iron source, this is ideal for intense, stable beams, but the ECR works by forming a plasma inside the iron source. Now, as you form the plasma, you touch the walls of the iron source, and as a result, you strip things from the outside, things like cadmium. For example, cadmium is often used in paint, so it was probably at the painting of the inside of the iron source. And these end up in your beam. They have the same mass to charge, so they end up in the same beam. Now, if you had a stable beam, this wouldn't be an issue at all. You know, you would have many, many times more beam particles than these contaminants. When you're dealing with a radioactive beam of the order 10 to the 4, maybe 10 to the 3 particles per second, these are the same order or more intense than your beam of interest. So you really need this CHICO setup where you can distinguish by time of flight, time difference, in order to be able to separate the thing of interest at all. And the resulting gamma spectrum from the 2017 work is shown just there. So just to summarize this in one quick slide before moving on to the new stuff. These were the results. We measured one quadrupole moment for the first 2+ state, but the key result was being able to determine this matrix element connecting the second 2+ and first 2+ state. And these were compared to 2 theoretical approaches. One simple triaxial rotor model, so it's a rigid triaxial rotor model. You assume some gamma that you fit to the experimental matrix elements, and you have no dispersion in gamma, and some beyond mean field calculations. And both reproduce the experimental data pretty well, so supporting this triaxial scenario with a gamma close to 30 degrees. But from the experimental results, it wasn't possible to determine this gamma. The set of matrix elements we obtained was just not sufficient in order to be able to do that with any confidence. Now, you can come up with a value, but you have to make certain assumptions about matrix elements in order to do that. So it wasn't published in this particular paper. So we returned to look at this again. So the CARIBU setup was significantly upgraded. And those upgrades were a new CARIBU source. This was useful as it allowed us to increase the beam intensity, which is always a useful thing. We had 11 Gratina modules now instead of the 8 that the previous experiment was performed with, so the efficiency is greater. But the key technical development was using an EBIS instead of an ECR charge breeder. So the result of this is you have significantly less contamination, resulting in a much less complex gamma ray spectrum that's not contaminated by all of these contaminants from the ECR. And in principle, that gives you access to backscattering data, which is very useful in Coulomb-excitation analysis, but it didn't quite work out that way, as I'll address in a second. So these are the results from the 2018 experiment. And I think the most interesting way to show them is a direct comparison to the spectrum obtained beforehand. So this is less beam on target data. It's only 60 hours or so, but you can see the quality of the spectrum is increased massively, both in terms of yield and cleanliness. We see new transitions that were not new in ruthenium, but transitions unobserved in this study. For example, this 8 to 6 ERAS transition, which is just not visible in this spectrum. So the number of matrix elements we obtain is expanded. And this is all as a result of this much nicer Chico spectrum you can see just here. Now the spectrum only has two features. This is the scattered ruthenium just here and the scattered lead at the top. So there's no contamination from these stable things with the same mass to charge as in the previous run. Just here, and there was sort of a few curiosities in this measurement. Gamma ray spectrum itself looks very nice, but there's a few things I've marked with a question mark. And what these are, I think, are some collective states in contamination that happens to be radioactive contamination in the mass 110 beam. So it's not just ruthenium 110 that comes out of the CARIBU source. You also have other unstable mass 110. You know, the bending power of the separating power of the magnet is not sufficient to extract or to separate all of those. So in something like technetium 110 or rhodium 110, there's some collective state or isomer or something that's also excited, giving rise to these two lines just here. Now, why this puzzled us so much is that we also took this very large amount of decay data. So this is looking at the decay of the radioactive beam inside Gratina with the aim of measuring branching ratios and mixing ratios. And these two lines happen not to be present in this decay data. So it's stuff that's only populated in Coulomb-excitation, is completely unknown to the nuclear database. Now, I mentioned with this EBIS source that this should give us access to backscattering data, where we don't have this coincidence between the left and right hemispheres due to the cleaner beam. But actually, unfortunately, in this experiment, that couldn't be done because it was found that the backward windows of the PPAC detector were contaminated with californium. So even applying some time gate between the EBIS, you still weren't able to use this information. But it's not so critical, really. You see, even only measuring up to 90 degrees in the lab, you still cover center of mass angles of the greater than 100 degrees, up to 120 degrees in the center of mass. So you're really sensitive to these second order effects, the reorientation effect, etc. So as I mentioned, decay data was taken. And this is, I think, one real lesson we learned on this experiment, that when you're doing these Coulomb studies, it really helps to have complementary decay data as well. This is a very simple setup. It's just implanting the cocktail beam onto a gold foil in the center of Gratina. There's no active stopper or anything. It's helped by having excellent angular coverage in Gratina, and the aim really was to measure precise branching ratios to use in the Gosha analysis, and if possible, but it's much more difficult, to measure E2-M1 mixing ratios. As in our previous analysis, we assume that everything is E2, which, although we suspect is the case, needn't necessarily be true. So this is just a snapshot of what we saw, and it's quite extraordinary, I think, that you see such a complicated level scheme built up from such a small amount of decay data. You know, the beam intensities are not enormous. Nevertheless, you can build up something of real complexity, I think. But what we're really interested in is being able to measure branching ratios for these low-lying states down here, and if possible, these E2-M1 mixing ratios, which I show here. So this is an example from our molybdenum 106 data. This is analysis performed both by myself, by Mitch Almond at Argonne, and also our PhD student Shaheen Jazravi. And the result for this molybdenum case is that we have a mixing ratio that's strongly consistent with about 95% E2 between these 2-to-2 transitions. So supporting our assumption in the initial analysis that these things were dominated by the E2 component. Okay, so what's the new information then from this study? Well, I flashed that up here. You saw in the gamma ray spectrum there were these two new gamma rays in ruthenium 110. So we can publish matrix elements for these levels. But as a result of this beta decay data, we also have these branching ratios. So for example, looking at this second 4+ state, we only measure this transition in Coulomb-ex, but we measure these two in the beta decay. So being able to fix this transition and knowing these two branching ratios enables us to publish matrix elements for these states as well. So we've significantly expanded the set of matrix elements that we're able to present from this data. These were analyzed with the Gosha code that was mentioned earlier. So very briefly, what Gosha does is it's a chi-squared search code. So we provide our experimental gamma ray yields as well as other spectroscopic data such as the branching ratios we either get from the literature or we determine in our experiment, the lifetimes if they're known, as well as facets of the experiment such as the gamma ray detection angles, modeling the stopping of the ions in the target, and we fit this to the experimental yields and find the set of matrix elements that best reproduces this data. And this I present just here. Now the things to note here are that the matrix elements have improved precision over our earlier set of data, which is good, and they're also expanded. But the key result for us is that we have now quadrupole moments for both the first 2+ state and the second 2+ state. They have opposite sign, as one would expect. And as a result of that and our sensitivity to the signs, the interference between these matrix elements, we can also publish one of these controversial gamma values and beta values that were discussed earlier. I should add a note, I think, that the M1 matrix elements, so in principle, we can determine the mixing ratio from this from our decay data. In the case of this nucleus, that turned out not to be possible. And the reason for that was just some contaminant transition. But we were fortunate that previous work had been done in this Eldridge EPGA from 2018. So using Californium source inside gamma sphere, and they had been able to determine the mixing ratio, which happened to support our previous conclusions that it's completely dominated by this E2 component. So it's actually their mixing ratio we use in the analysis and not one we've determined ourselves. So what about the sum rules then that we've used to get these beta and gamma parameters? So briefly what they are, the Q-squared invariance related to this beta. So here you have to have knowledge of matrix elements connecting the ground state to 2+ states. And for this gamma value, which is the thing that hints at this triaxial deformation, we need to know a richer set of matrix elements. We need to know both the matrix elements connecting the ground state and 2+ states, as well as the matrix elements connecting 2+ states to other 2+ states. So I add a few comments on it just here. I mean, the natural question is, do we have enough matrix elements to determine these shape parameters reliably? I should say this is the central value, of course, of these matrix elements. I'll comment on the spread in these matrix elements in a second. This was demonstrated by Jack Henderson in this very recent paper in 2020, where I pinched this figure from just here. You get convergence quite rapidly. So in Jack's paper, he used a set of matrix elements determined, I think, with new shell X, and shown that this convergence for these central values was reached pretty rapidly. So although we don't observe a third 2+ state, in our data, we're just sort of linked. We just have this 0+ state and the first 2 2+ states. We don't expect this contribution from the third 2+ state to be significant. And indeed, that was shown by the Warsaw group experimentally. For this case of molybdenum 100, they were able to show that the contribution from the third 2+ state to this gamma value was pretty limited as well. So the question is then, what about the dispersion in this gamma? So as was discussed earlier, this is a much higher order invariance, so needs a massively greater set of matrix elements, which we clearly don't have experimentally. So the way we can attempt to address this is to perhaps use the theoretical matrix elements. So in Jack's paper, he made use of these matrix elements from new shell X. In our case, our theoretical matrix elements come from beyond mean field calculations. So we can attempt to do the same analysis with this set of matrix elements from beyond mean field calculations and estimate it that way. These are also, I should say, very deformed nuclei, so there's perhaps a greater chance that these gamma values have more limited dispersion than in some of the cases presented earlier. And I just sort of flashed this up as information, really, for a recent example where we've made use of quadrupole sum rules analysis in order to determine triaxial deformation. See this case of 130 xenon. This was analysis led by Lisa Morrison, who's a PhD student at the University of Surrey. This is a really nice paper that's using a contaminant from a high Isolde beam. Xenon 130 is stable, and with this sort of short amount of data, we're able to determine these matrix elements to support the triaxial deformation of 130 xenon. So these are results that we have both experimentally and are supported by shell model calculations, calculations with the Bohr Hamiltonian, as well as approaches with simple phenomenological models. I probably don't have time to discuss this in any detail, and since I'm not leading this analysis myself, I shouldn't say too much about it. But in addition to these ruthenium cases, we also have massively improved data for 104 and 106 molybdenum. And there's the nice case that you've measured two neighbouring even mass nuclei, so you can sort of tell a story between the two. So what about the outlook then? This is not a campaign of experiments that's finished. We hope that when things eventually get back to normal, fingers crossed, there's a chance that we'll run these experiments again next year. So these experiments will look at zirconium 100, hopefully ruthenium 112 should the yield be sufficient. Now, this is a potential sign of both maximum triaxiality and oblate deformation, as well as this palladium case that Alison highlighted earlier. We've seen that the power of complementary data to support our Coulomb studies. And having this beta decay data massively improves your set of matrix elements, and we often find discrepancies with branching ratios and things in the literature that are difficult to reconcile with just Coulomb data. With these, we have the same as before. We have this access to backscattering data, hopefully, as long as we don't have more Chico contamination, with the possibility of determining these gamma parameters for these nuclei. I should just say further in the future, CARIBU will be no more eventually. They will not produce another CARIBU source. What they will do instead is a setup called new CARIBU. So this is neutron-induced fission of uranium. This, unfortunately, for those of us interested in these gamma soft nuclei, is not so useful as this shifts the mass yields. So instead of being focused on things like barium close to mass 140 and these mass 110 nuclei, you now shift it to closer to tin 132. So it's very useful for people interested in that. But there's some possibility of extracting refractory isotopes at facilities such as Isolde. So for the approach, as far as I understand, that they're taking is to try and produce molecules of these radioactive refractory isotopes that can be extracted from the isol target, then to break apart these molecules inside the EBIS, as is normally done with many beams, giving access to these sort of beams at facilities like Isolde. And I think that's all I would like to say. So thank you very much for your attention.
Thank you very much, Dan, for another beautiful talk at TASTE. You explain things so beautifully. So we have time for a question. Alfredo,
I've got 8 questions.
I think it's an easy one. Oh. Alfredo Pova is asking about the errors in beta and gamma.
That's right, yeah.
Statistical errors, or?
That's correct. So they're just the errors from the statistical errors in our E2 matrix elements.
And I was thinking about M1s being populated in what kind of bombarding energies do you have? Do you have relativistic energies, or why do you have M1 contributions, you think?
No, so it's just the M1 bit is there. We only excite via E2, but you can decay via M1. Right. So some of the yield you're seeing could be from the decay of the M1 part of the decay. So you need to know this in your Gosha bit.
Right. Okay, Dan, thank you so much for.
Hang on, I've got some questions. Sorry.
Who was the question?
Hi, Peter.
Peter Butler. All right.
Thanks. Yes, very nice talk, Dan. Beautiful results, and congratulations on getting a value of gamma. Just to confirm, of course, as you alluded to in your talk, that you're measuring a mean value of gamma with an error bar, but you're not at this stage. I guess one needs more intensity from radioactive beams to go further the next moment to tell the difference between whether it's gamma soft or gamma rigid.
Exactly, yes.
Yeah.
I mean, the set of matrix elements is intimidating, I think, that one needs in order to do that.
Exactly, but something for EFRID maybe. The other thing, I mean, what I'd really like to highlight, this beautiful comparison you made between the two different types of charge breather.
I'll put this up,
and
yeah.
between the EBIS and the ECR. And I think that that really does tell anybody who's building radioactive beam facilities in the future, or even in the present, that they really should throw away their ECR source. There's no doubt about that. You had these unidentified gamma transitions in the spectrum. Have you tried doing gamma analysis? I mean, you might think it's impossible, but
yeah, we have. So you mean sort of particle gamma? So
yeah, particle gamma.
Yeah. So the problem is that they're not in coincidence with each other. I think
it's with anything else though.
No, it looks like two collective states, and we can't even say what nucleus they're in.
Right. Okay. So it doesn't fit the 2+ or anything like that.
Yeah.
Oh, okay. All right. That's fine.
Probably, in a really well set up experiment, what one would have to do is investigate with things like the EBIS settings or something at the time of the experiment, see how that changes the yields.
Yeah. Okay. All right. Thanks very much. Very nice. Thank you.
Yeah. Thank you, Peter. Cheers.
Any other questions? I don't want to miss anyone. Alfredo, you want to say something?
No, he has answered me.
Excellent.
It's perfectly.
So,
I wanted just to know that it was. Well, this is a very long discussion, but one thing I wanted to ask you, just to put the things, what you measure is what you measure.
That's right.
This is the reality. Sometimes we have the problem of how to name that. In many cases, we need to have a semantics that is familiar to us, and this brings us sometimes too far into the semi-classical regime, because it's not very easy to give names to phenomena which are radically quantum, because we don't live there. We don't buy the bread in a quantum patisserie.
Okay, I think we're going to stop here because my DVC research is waiting. I don't want to have to wait for too long, otherwise I'm going to be in trouble. So we have the Women in Science next, but before, thank you so much, all the speakers, and again, beautiful talks by everyone.